So when I went to school,
and
I know that was a long time ago, and you're probably surprised they even had electronics back then. When we would do something like what we did yesterday, which was to describe the electric potential around a point charge. And by the way, I never did any of this in high school. I had to wait till college to do all of this. So you guys are already way smarter than I. We are talking about, the electric potential at some point here. And we talked about measuring it from infinity to a place close by. And I want to remind you of some of the things we talked about to get there, just real briefly. We said that we were going to calculate the work done in moving the particle, which meant we would have to do something on the order of this, right? And then I reminded you that, we're dealing with a point charge, so we could deal with the force on the point charge while moving it through that electric field. We made that substitution. And then I said, if I wanted to do electric potential, I could divide both sides by Q here. And from there, we would calculate the work done, or the electric potential, either one. I want to stop right here. When I was in school, I was taught that dr in this circumstance was supposed to represent the incremental change in position as I traveled from infinity to the point in question. That's what I was taught in school. So what I was taught to do is consider a point, say right here, that's in that transition where this is R and this is one of the R's that I would be using on my way from infinity to R. Everybody okay so far with what I'm saying? So this is just one location. At that point, if I was doing a sum, the force on that particle is this direction. That's Q times E, the force on that particle. But I'm going to move the particle this way, a small dr. Does that make sense so far what I'm saying? This is not a massive difference. And I know some of you would prefer I just cut to the chase and just tell you what you need to know. But some of you are going to do this kind of stuff for a living. So I need to make sure you fully appreciate what I'm about to say. If you do it this way, even if we went the extra mile and divided out by Q already, and we're doing this calculation, the dot product would have produced a cosine of 180 degrees. Right? Because the force that is here is acting in one direction, but the change in displacement is in another. This is one way to think about this problem. Now, the problem with that is that over time, consistency becomes an issue. If you're going to do it this way, you have to change some of the other things that you think about. Like, this might be the direction that the force is acting on the particle, but the work done here, is this work being done against the particle? Who's doing the work? Is it me? Am I doing the work, pushing the particle there? Or are we just looking at the absolute change in work being done? These are all questions that have kind of a gray area answer, because nobody's actually moving the particle, right? We're just talking about the difference in potential between two places. So over the course of a couple of years, and I looked up 3 different books on this day before yesterday, and there's different things in each one of those books. So I have a choice on how to present this to you. And yesterday we presented it as dr points in the direction of r hat as it appears in our statement of the electric field, meaning the electric field is k q over r squared r hat, with r hat being in the radial direction of the particle. So, as a standard, what we're going to do from this point forward is state that the electric potential isn't looking at the work done on the particle, but is looking at the change in potential energy per unit charge. And the reason we're going to do this is because we want the electric potential to be more reflective of energy and less reflective of what's being done to the particle by an external source. You too. This doesn't change very much, but it does change something important that I need to kind of put in place, okay? So by making this change, that we're going to say that the electric potential is the change in electric potential energy per unit charge instead of the work done per unit charge. It does one meager thing. And that is, we have to remember that the change in potential energy is negative the work done on the particle. What this does for us is it removes the agent from the problem. Now, I've used this word only sparingly. The agent would be the thing that moved the particle from infinity to this location. It removes that and makes the whole thing just about the differences in the two locations. That's what it does. But it does something else important, and this is where I'm just going to kind of move a little quickly. This is still how the work is calculated, except we go back to referencing it based on dr pointing in the direction of the electric field, which makes this cosine 0 degrees. Of course, I can pull the Q out, and I'm still going to be integrating the electric field, which is KQ over R squared times dr times the cosine of 0 degrees. We know the result of this integral, but just to be expedient, it's going to be KQ over R with a negative sign that we get due to the antiderivative property, evaluated from infinity to R. And lastly, we get minus KQQ over R, capital R, as the work done moving the particle from infinity to here. But the electric potential is minus the work done. So, in order to calculate the electric potential, I take my work, put it here, that becomes delta U. So delta U is minus negative KQQ over R. And electric potential is KQQ over R divided by Q, which leaves me with KQ over R. Now that's a long route, so let's get some shortcuts in here for what we're going to accept as the calculation for electric potential. This is just fixing yesterday and ensuring we get an electric potential that's positive, and I'll explain why this must be true. Okay? So first, consider, do you think the object should have gained energy or lost energy as it went from infinity to a place close to the charge? Do you understand what I mean by this? I would expect that if I'm getting close to the charge and the charge is pushing me away, it should gain energy, potential energy. It's like, when I try to lift something away from the earth, right? It wants to go back to being closer to the earth. Lifting it requires me to do something. It gains energy as I move it away from the earth. Because if I let go, it's going to come back down. Well, if I put a positive particle here, isn't it going to be pushed away from that location? So getting closer, I think, means it's going to take more energy. So I would expect the change in potential energy to be positive as I get closer to the particle, and I expect the change in potential to be positive as I get closer to the particle. So I'm going to expect that I have a positive answer here. Remember, the idea here is we're trying to come up with a way of discussing something that we can all agree upon when it comes to the reasonableness of how a situation should exist. And it takes work to get a particle up close to another positive particle. That's what this is trying to express, which is why this answer has to be positive when we're all done. Now, I'm not just trying to arm wave. What I'm trying to do is say we're going to make some distinctions, and I'm going to put all of it together. Work is equal to the integral of f dot dx. Change in potential energy is equal to minus the work done. Yeah. Is fixed in place, right? And I want to move this this is a positive charge, so let me make sure we have an understanding. This is positive, okay? I want to move this positive charge close to this charge. Okay? And let's be really clear. This is positive as well. Okay. Right now, this moment, there's no, oops, I don't want to do that. There's an electric field this way pointing away from that charge, correct? If I bring this charge up here, I have to apply a force just to hold it in place, right? In fact, so for me, I have to apply a force this way to hold it, because if I don't, it'll shoot off to the right. But that's me. I'm the agent. If I do work on the particle, I would be doing positive work on the particle for me to push it. We're not asking about, and this is why we're having this conversation. And I don't know that I'm doing a great job explaining it either. That's why I'm trying desperately to correct myself. I do positive work on the particle. That means I lose energy. I'm the one losing the energy. So remember, if I do positive work, I lose energy. That's what this says. Okay. I'm working against the electric field. If I'm doing positive work, the electric field is pushing this way the whole time I'm trying to put the particle towards the other particle. So although I'm doing positive work on the particle, the field is doing negative work on the particle. Does that make sense? Yeah, so I think it's a hard concept because it's not like the field is doing anything. Right? The field's just there in space pushing on the particle. This conversation is to indicate that we're trying to track the flow of energy, and make no mistake. Remember, this is humans trying to put mathematical relationships together to describe what happens in nature. You understand what I'm trying to say?
Yeah, so everything's relative to like whatever is like pushing it closer? Or like whatever forces?
The particle can't push itself.
Yeah.
Okay? So what I'm describing is that if I want to move the particle, me, I am the agent. I am something external to the story. I would have to push this way on the particle. That would be positive work by me on the particle because I'm pushing it to the left and it's going to the left, so the work would be positive. But every force can do work. So at the same time that I'm doing positive work, the electric force is doing negative work. Because the electric force is pushing to the right, but the particle's going to the left. Okay? So while I'm doing positive work, negative work is being done on the particle by the field. Is that Okay?
It's the work done by the field onto the particle.
Yes.
How does this like be helpful?
Yes. What we're trying to do is build a way to mathematically describe the fact that the particle's potential energy has increased due to its change in position. But we don't want to make it about the agent that caused that change. We're trying to make it only about the location in space where the particle's position has changed. That's why it's such a weird, quirky math thing. And for those of you who are full-blown lost, or like the three of you who have just stopped paying attention, let me at least boil this down to something, okay? To do that, I want to get this out of the way for a minute. This statement here, let's leave it up here for a minute. Work is defined like this. Force from an electric field is defined like this. And we're defining electric potential like this. We can combine all of these all at one time, right? Just a series of substitutions. For example, my first substitution could be this. My next substitution could be this. If I do that, I'll get that's me just taking these two things and subbing them in. And my last substitution would be today, in our current universe, this is how we choose to define the electric potential and remove the agent that moves the particle out of the relationship completely and make this purely about the change in position. The only distinction between this and what you'll see on an equation sheet is that they generally now write this in terms of R for a generic indicator of change in position. And even though I kind of rehearsed what I wanted to say today, I feel like I still didn't do a great job of it. So let me help clarify this. I want you to kind of use your imagination for a minute, okay? You guys are pretty smart people, I think. In fact, I'm often amazed that you guys are doing this in high school. If you plot the electric field of a point particle, we get something that looks like this, right? That's the electric field of a point particle. All good? It's kind of telling us that the closer we get to the particle, the harder it is to keep getting closer to the particle. Does that make sense? Now, hear me out. At the same time, we just talked about the idea that if I wanted to bring a particle from far away and get it closer and closer, you realize that that particle, as I get it closer and closer, is going to require, or is going to be experiencing a larger and larger and larger and larger force to get there. Does that make sense? Well, at the same time, we solved a minute ago the electric potential. The electric potential is a little different than the electric field, though. The electric potential doesn't have direction. The electric potential just tells us, like we said the other day, the electric potential kind of tells us, remember, it's going to be 1 over r, so 1 over r is like 1 over r squared, but doesn't decay as fast, right? So I don't have it decaying as fast. This is me trying to represent this for the electric potential. Now, I tried to tell you that electric potential is kind of like a set of stairs, that there's no energy on the stairs. But if you place an object at a stair, then you kind of know that some stairs would have less energy than other stairs. Remember that argument? Now, I think if you didn't know that this was a plot of electric potential, and you thought that, well, maybe this is just, a hill. It would be clear to you, right, that putting a ball here would have less energy than putting the ball here, right, for the same ball. However, if I let the ball go here, do you know which direction the ball would roll? Would it, if this was a hill, would the ball roll to the right or to the left? It would roll downhill. Electric potential is telling you not just about the amount of energy, but it tells you what the particle will do in a region of space in a similar way that the electric field will. Take a look at this for a minute and consider doing just a little bit of math on it. First math I want to do is this. Take away the integral sign and leave this as dV. I'm going to divide both sides by dr and ignore the fact that that's a dot product. And I'm going to put the negative on the other side. Now, there's two things indicated here. The first is that dV/dr tells you the size of the electric field, the steepness of the electric field. However, the negative sign indicates that the direction of the electric field would be in the opposite direction of the slope. Now, if I bring back in my axes for a minute, point 1, point 2, point 3. Is a slope at point 1 positive or negative? Negative. But that tells me that the point at slope 1 must relate to an electric field that's positive. At point 2, is the slope positive or negative? At point 2, is the slope positive or negative? Negative. Is it greater than or less than the slope at point 1? Less. That indicates that the electric field is smaller than at point 1, but the direction of the electric field is still positive. At point 3, is the slope positive or negative? Still negative. But the electric field is going to be still pointing away, but smaller, because the slope is smaller. The electric potential is like, the way I like to describe it, it's like if we were to compare it to something that is tangible. The electric potential is like elevation. If you have a high electric potential, it's like having a large hill in an area around you. You would have to expend energy to get something to the top of that hill, because naturally things would like to flow away from the top of that hill. I put a pebble on the top of a hill, just give it a nudge, and it'll fall off the hill, right? Or roll down to the bottom. So the electric potential is something that tells you about the electric field, but it tells it from the standpoint of energy as opposed to telling you about it from the standpoint of force. Electric fields have been largely about forces on particles, but electric potentials are all about energy. Electric potentials don't necessarily contain any information about direction, but they do contain information about how much energy is required to move from one place to the other. Now,